has two variable capacitors instead of a variable inductor and a variable capacitor. Variable inductors are expensive.
Yes, they are.
So that one works really well, and you can use it as a balun at the same time. Let's see, should I show you the pictures first? Yeah, how about that? If I take a magnet and put it on my tank circuit, that will charge up immediately. It will charge up the capacitor. Gradually, the inductor charges up by discharging the capacitor. Second slide already, second picture already. As it goes on, and also notice the polarity of that capacitor in the first slide, or the first image. Because what happens after you charge it with the battery, you remove the battery, and now the capacitor is charging up the inductor to create a magnetic field. The current keeps flowing, it keeps flowing, and more of the capacitor's charge is going away. All of a sudden, you're starting to see a little bit different. Let's see. Yes, positive, negative. And now we've gotten to the point where the inductive field is at the strongest, capacitive field is at the weakest. And if you'll notice, the current direction changed and the polarity of the capacitor flopped. Well, what happened here? We have back EMF now. All of a sudden, our inductor's field is collapsing, creating current in just the opposite direction at just the opposite voltage, and it's charging up our capacitor. So what was going into the inductor and making that nice field is now the field is collapsing, going in the opposite direction and charging a capacitor in the opposite polarity. This goes on for a cycle, and we're back to where we started. At the very bottom, we have plus on the top, minus on the bottom of the capacitor. This can go on forever, except in the real world, we have imperfect resistors, or imperfect conductors, imperfect inductors, imperfect capacitors. We have resistance, we have other effects taking place, and eventually this dies out. But for maybe even a second, this will keep occurring. That's why in a real circuit, you keep getting fed by your oscillator at a certain positive feedback. I was wrong. Positive feedback, slight amount of positive feedback through an amplifier, and that's feeding this tank circuit. So they're pretty amazing little gadgets. If you want, we can go through it in words, but the pictures, I think, tell the story a little bit better than those words do. Basically, it changes, it takes the capacitor, which charges up immediately. Inductors don't like to charge up immediately, but they don't like to discharge, so what happens is that magnetic field dies slowly, feeding the capacitor.
This is more a picture of this really is, if you charge the capacitor up with the switch open to the inductor, take the battery away, close the switch to the inductor, and it sits there, and it rings back and forth.
You don't really even need that switch to take this.
I know, but it's more impressive when you
really, it is like a bell. It's like a pendulum. Basically, like you need to add a little bit to that pendulum every single time because of friction. Here, you need to add just a little kick every few milliseconds to keep this thing going. But the amazing part is this is the thing that keeps the pendulum. This is the pendulum. It keeps going on its own. Here's a cool little thing. But this is what I was explaining is that for the final transformer in your transmitter is actually looks like a tank coil to a capacitor. The capacitor is your antenna, which radiates that magnetic field. So I thought this graphic was really appropriate for taking us from tank circuits to that's our antenna. So you're capacitively coupling to the ether, which doesn't really
and you've got magnetic lines coming off the ends.
Yeah, I know, you're wasting that.
The end effect.
Now, does anybody want a break? Because we're now just going to change subject.
They're not ready for a break yet, huh?
You were shaking head, yes.
Do you need a break?
I don't care. Go for it.
If you want to take a break, take 5 minutes. I need to drink some water.
I know that.
Yeah, you need to know what's going on. And we happen to be at one, let's see, it is the most quiet minimum in 100 years. We might be going for a record for the longest minimum, too. We only have to go another year. And then, is anyone not here?
Whoever's not here, please raise their hand.
Not all there? Yeah, he's not all there. So Rob, how's it going?
I said you practice and see how tough it is.
Are you taking notes? I'm going to put this on the web, so I mean, I know it's right. You said that.
Yeah, it helps you.
I didn't expect you to write all this down. I wasn't going to give you a final exam when we were done, although...
Don't even think about it.
Well, you can give us one whether or not we take it.
Yeah. Well, that'll make you...
Offer certificates, they'll take it.
Can make it a little like I'm a propagation expert card or something like that. My MTS card, my other two.
Just a cert, okay.
Well, you
Okay,
guys
I'm going to get going then.
sporadic ease.
Kurt doesn't need to know this, does he? These are basically VHF, UHF propagation modes. There are many other propagation modes which I've eliminated for medium wave, long wave, and ultralight, ELF, and stuff like that. We don't need those. Here he comes. I just wanted to make sure that this was for ecom and trying to make it specific to Aries. If I give this talk to some other group, I might add those back in. Now remember, refraction and reflection are basically two sides of the very same coin, and they're very, very, very similar. So when we get to tropoducting and troposcatter, basically it's just fine gradations between reflection and refraction of how changeable and how distinct the layer is. The difference in the way it bends. It's very sensitive. But we have meteor scatter, which is real interesting. I was sitting in grad school in a class, and here's the professor right there. I was in the front row. My friend was sitting there, and he's pushing a QSL card at me. And I'm going, okay, great. Here's 2 meters. No, I didn't see 2 meters. I saw, oh, you work North Dakota. Great. It pokes me again. And I'm going, 2 meters, North Dakota. We're in New Mexico. What? And the professor's looking at us. He's lecturing us, and we're going, this is a full professor, by the way, not just one of these associates. My friend's poking me, and I'm going, this is the first day of class. We've got to pay attention. Look at this. Okay, you got North Dakota. Meteor scatter. So he worked for an hour through meteor shower to try to work North Dakota. And what you do is you use burst CW, which is really high speed CW. You're sending your call, and your grid square. Basically, what is it? A Maidenhead grid square. So it's 4 characters, shows right where you are. And all he's sending is his call sign grid square at, I think, 100 words a minute. The guy on the other end is recording this and then decoding it on his computer to get, okay, and then he sends the same thing back, his call sign, his grid square. All you need to do is get in both directions and you made a contact. But what they're trying to do is when the meteor hits the atmosphere, it burns up and it leaves a long trail of ions. You're bouncing off those ions, which are up to 80 to 100 miles high. So for 2 meters, he was bouncing off these meteor scatters, which last sometimes as long as 15 seconds, normally only a second. So he was hitting just parts of these and making contact with his friend in North Dakota. So very strange stuff. Auroral scattering is a lot easier, but aurora can be very steady or it can be very, very rapidly moving. So depending upon the type of auroral activity that's going on, this could be easy or it could be really, really difficult. On CW, you can tell when you're working over the pole because you can hear the aurora going on, and it sounds like you're hearing when you're swimming